Hello everyone, welcome back to Labtube. In this video I'm going to do question 16 from section 16.5. The question asks to determine whether or not the vector field given there is conservative or not. If it is conservative, find a potential function for that vector field. Okay, let me first recall that a vector field F is conservative. What does conservative vector field mean? It means, i.e., there exists a potential function F such that gradient of that function is equal to your vector field. Such function exists if and only if it is very easy. You find curl of F. If it is 0, then you can find potential function. Okay, so let's check this for this vector field. My vector field is given there, and I have to find curl of F. What is curl of F? Curl of F is cross product of nabla to F. So I have two vectors. Nabla vector is ddx, ddy, dz. And F is given by this. The first component is 1, second component is sine z, third component is y cosine z. Now find the cross product. So this times means that find partial derivative of y, this with respect to y. So the first component is going to be cosine z minus this with respect to that, cosine z. Now the second component, this with respect to this is 0, so this with respect to z, and minus this with respect to x, it is 0. Now the third one, this with respect to x is 0, this with respect to x is 0. So the vector field that has 0 curl. That means F is so F is a conservative, and now we have to find a potential function. What is potential function? So we are looking for a function f(x, y, z) such that gradient of that function. What is gradient? Gradient is a vector field with 3 components. First component is fx, fy, and fz. The gradient of that function is equal to our vector field, which is 1 sine z and y cosine z. I have 2 vectors, they are equal. That means fx, first component is equal to first component. Second component is equal to second component. And third component is equal to third component. Okay, I'm looking for such f. What does it mean? The first one. Let's start with the first one. And the first one means that if I integrate this with respect to x, I will get f. So my function is of this form. Antiderivative of 1 is x plus any constant with respect to x. Any constant with respect to x means it's just constant, it's a function of y, or it's a function of y and z. So I can have this form. Okay, that's the form of my function. Now I can find partial derivative of this with respect to y. It is going to be 0 plus partial derivative of c with respect to y. Why did I do that? Because I know already what is partial derivative of f with respect to y. That means these two should be equal, and then that means that cy is equal to sine z. What does it mean? Cy, partial derivative of c with respect to y is equal to sine z. That means c yz, the function, is equal to y times sine z plus any function in terms of z. So dz. Okay, great. So my function, now I can update it. It is of this form, x plus y sine z plus a constant. Let me, instead of d, put c. Oh, no, actually d is good one. So dz. Okay, now if I do find partial derivative of this with respect to z, so f z is going to be 0 plus y cosine z plus d prime. Why did I do that? Because I already know what is fz, and that means I already have this part. That means d prime is 0. That means d is just constant. Okay, what is the result? The result is this. If I have a function of this form, a function x plus y sine z plus any constant you want. If you have such function, if you find gradient of that function, it is going to be the vector field given here. That means f is a potential of. Okay, very quick wrap up. You check a vector field in R3 is conservative by checking its curl. If curl is 0, that means it's conservative. What does conservative mean? Conservative means you can find a function whose gradient is equal to your vector field. Okay, to find that we did this gymnastics, so we are looking for f such that this is equal to that, and then step by step figured out that the general form of potential function for that vector field would be this. Thank you for watching this video.